Hi everyone, welcome back to the channel. I'm Hussein Younes, and in today's video we're going to zoom out a little bit from our series on building AI agents from scratch, and we're going to explain some very important and critical concepts in LangGraph that's going to help us understand a little bit in depth what's going on, what's happening in LangGraph. And by understanding these concepts, it's going to be much easier for us to move forward in the future with broader concepts and higher level concepts. So these concepts that I'm going to explain today are low level concepts. So by understanding it, hopefully we can understand the higher level concepts. And when building real life examples, we're going to have like the solid understanding of what's going on, and it's going to be easier for us to debug in the future workflows and to build more complex workflows in general. So without further ado, let's move on. In this episode, I'm going to explain two main concepts: graphs and states. So how to define like the graph, basically, and some concepts that we're going to see in a moment, and the state, how the state gets updated, how it gets manipulated, how we can define the state, how we can break the state into multiple states. So we're going to see that. So first, the setup. So I have just like some imports, Python imports, and now let's start with the graph. So first, what is a graph? LangGraph in general models the workflows, the agentic workflows as graphs. And think of it like just like a flow chart, right? So nodes are the boxes or the functions that do the work. Edges are basically the arrows between the nodes, and the state is the data that flows between the nodes. So here is a simple example that we have. We have start node, like it's just a sequential linear workflow. So now how the graph executes. So the concept of super steps. So LangGraph in general implements the concept of message passing. So message passing was inspired by Google's Pergel system. So it's a system that has been introduced by Google in 2010 to process large distributed graphs, and it executes in super steps, right? So this is what also LangGraph adopts. So a super step is just iteration over the nodes in the graph. So every step of execution, it's called a super step. So nodes that are in parallel, they run in the same super step, right? Because they are in parallel. I'm going to show you how that works in a moment. And sequential nodes, they run in separate super steps. So for example, every node here is going to run in a separate super step. But if we had another node here, C, like in parallel with B, it's going to be in the same super step with B. So let's take a look at this example. So we have a simple state here. It has just one value, which is an integer, a number, right? And here we have three nodes: node A, node B, node C. Node A, it takes the value and adds 1 to it. Node B multiplies it by 2. Node C adds 10 to it. We add the nodes, right? And we add the edges between the nodes in a sequential manner. So we have node A, then node B, then node C. Then we compile the graph, and now we invoke the graph. So we call the graph with the value 5. So the beginning, we just give the initial value of the value variable is going to be 5. Then it's going to get passed throughout the graph. So now let's see the final result. Every node we're going to print executing node A, executing node B, executing node C. So here we see that we are executing sequentially. So executing node A, then executing node B, then node C, and the final value of the value variable, the result, is 22. Why 22? Because at the beginning it was 5, then we added 1 to it, 6, then multiplied by 2, 12, then added 10, 22, so the final value is 22. Now let's visualize the graph. If we visualize it, it's going to be just like this: start, A, B, C, and then end. Sequential workflow, right? So now let's see how parallel execution works. So parallel execution, we're gonna move this node B and make it in parallel with node C. So it's gonna be node A, node B, and node C. We add the edge from start to the start node. Then we add an edge from start node to parallel. Then we add an edge from start node to parallel 2. Parallel 1, parallel 2, so that they are in parallel. And the parallel nodes, they go to the end node. So now let's see, this is how it looks like. So we have start node, then parallel 1, then parallel 2, and then the end. And the state is the same. So it's just the same simple state, with just the value. So now let's run it. So now we get an error. The error says the key value can receive only one value per step. So this is very important thing to understand. So at every super step, any value in any variable in the state should have exclusively one value. At the beginning of the start node, we know that the value of value was 5, right? Because we passed 5 at the beginning. But then when we went and then start node, what does it do? It adds, it's just node A, so it adds 1 to the value, so it becomes 6, right? And after this node, the value becomes 6. But at this node, the value here in parallel 1, it is node B, so it becomes, it multiplies by 2, so it becomes 12. But in this one, we add 10 to it, so it becomes 16. So here we have 12, and here we have 16. Therefore, we have a confusion here. If we want to return, do we return the value 12 or do we return the value 16? It's confusion. We don't know. That's why LangGraph returns an error and tells us every super step can receive one. Every value can have one value per step. So every variable in the state can have one value in a super step. Use annotated to handle multiple values. So we're going to learn what is annotated in a moment, which is a reducer, and then we can come back and see how we can fix this, right? But this is just a very important example for you to know that at every how LangGraph executes. So it first executes this in one step, then in the second step it executes this, and there it gets a confusion. Oh, should I multiply the value by 2, or should I just add 10 to it? Should I execute this one or this one? So it gets confusion because there is no way how to kind of aggregate the values. That's why it gets confused. Now let's go to the state. So how the state works. So what is a state? A state basically in LangGraph consists of two things. The schema, which is how the data looks like, what are the variables, what are the keys and values, and the reducers. Reducers, which are the functions that tell us how we update this variable throughout the graph. For example, here we didn't have a reducer. That's why we got this error because the graph got confused of how to deal with this value. So now we're gonna see how the state gets updated throughout the graph. So let's see a simple example. Here are 3 ways on how to define the state. It's not very important to know. You can just learn one of them. The most common one is a type dict. So this is just a dictionary in Python. There is another way to do it with a data class. So you can give it default values, and you can give it some other methods, helper methods to deal with the data. And if you also prefer to deal with the data like as objects rather than dictionaries, just a preference. Or you can use pydantic. So you can define the state as a pydantic model, which also gives data validation. So in runtime, it checks if the value basically complies with the type that you gave it in definition, right? We're just going to be using type dict for now. The first example, when we don't have reducers, let's see how the state gets updated. So here we have a state. Counter and message. We have 2 variables. One is an integer number and the other one is a string. So and then here we have 2 nodes. The first node basically updates the counter, makes it 10, and updates the message string and makes it hello. The second one only updates the counter and gives it value 20. So now we compile the graph. It will look something like this. Start node, then node 1, then node 2, so it's a sequential execution. We call the graph, we invoke the graph, we call it with a value, counter is 0, and message is start. So at the beginning, when we enter the node 1, right, it will go to node 1, and then here we print node 1, current state is counter is 0, so this is the initial state, and the message is start. After the execution of node 1, we go to node 2, so node 1 will update the state. So the counter will be 10 and the message will be hello, right? So we override the state. By default, if we don't have reducers, the state variables are going to get overwritten, right? So we can see it was here 0, then 10, here it was start, then hello. And at the end, after the node 2, it's going to be, the counter is going to be 20 and the message is going to be still hello because we haven't touched it here, right? Updates only the counter, the message stays the same. So this is how the state gets updated in LangGraph. This is very important to understand. Now let's see how we can use the reducers, right? So let's use a reducer with operation add. So to use the reducers, we use the class annotated. So we annotate the type using a function, and that function in this case is add. So now the counter type is annotated with the reducer, with the addition reducer, and the items is also annotated with the concatenation or addition also reducer, but addition for a list of strings. So this is a list, items is a list of strings, and the reducer is addition. So addition in lists is gonna just append or merge the lists, right? So the first node is going to be increment node. So we add 5 to the counter, and the items is going to be apple. In the add more nodes, the counter is going to be 3, and the item is going to be banana and cherry. And also here we have a sequential workflow, meaning that we're going to execute increment, then the second node, which is add more node. So now we compile it. The initial value, where initial values are 10 and orange. Then let's see what happens. At the beginning, the values are 10 and orange. Then we're going to increment. So when we increment, the current state is going to be at the beginning. Here we print. So before we do anything, it's just 10 and orange. Then it becomes, we increment with 5, so the counter becomes 15, 10 plus 5, 15. And the items are going to be orange and apple. So as you can see here, this didn't replace the items, it just added to it because we have the reducer add, right? After second node, we add 3 and we add these 2 items to the list. So the counter is going to be 18 and the items are going to be orange and apple plus banana and cherry. So we just add the items to the list. So this is very important to understand because we're going to be using these reducers, and we've already actually used them in our previous examples and our previous episodes, but we didn't understand what was that, what was like this annotated thing. But now we do. So now we have a special add message reducer by LangGraph, which applies to the list of messages. It merges lists of messages. Because like messages is the most common state variable in LangGraph, because we're building agents and workflows, and we're building conversational agents as well. So we need to save the list of messages and the conversation in the state. So add messages, as I told you, it just adds the list of messages together. So now let's see. So here we have 2 nodes, user node and AI node. We add them also sequentially. We have user, then AI. The first node adds the human message to the state. It's going to be appended to the empty state. At the beginning, we pass an empty state, right? Then we append a human message to it. Then we append the AI message to it. So let's just call the graph with the empty list of messages and see. And then we're going to print all the messages after we have executed this workflow. We're going to print all the messages. So in the states, in the state messages, we're going to have the human message hello, right? Because we added it here. And then we're going to have the message from the AI message, hi there, how can I help you? So again, we note that we don't replace the message because we have a reducer. The messages just get appended. So now the message state helper, again, because the messages are the most common state variable in LangGraph, they have actually created a message state class, like the built-in one. And you can just inherit from that message state and you can just add your other variables to it. So your my state is going to be like a message state by default. Okay, so now multiple state schemas. So this is also a good one. So let's say, for example, you have a state, but at the end of the state, you don't want to return the full state dictionary. You only want to return only some field of it, right? Some part of it. To do that, you can define an output schema and input schema. So the input schema is going to only have just one variable, which is the user input, and the output schema only going to have the final result. And any intermediate steps or intermediate variables they're not going to appear in the input or the output. Therefore, we put it in internal schema, which will hold the internal data that we don't want to expose to the output schema, for example. So you can, in this case, we have like 3 separate state schemas: input schema, output schema, and internal schema. And then here we have 2 nodes. Again, they are running sequentially, process and output. So the process input takes the input schema as input and returns the internal schema. The generate output, it takes the input internal schema and returns the output schema. So it's going to return only the result. We're not going to return the intermediate data or the user input, right, and to the output. So it's just helpful for us to separate the concerns for input and output and the internal graph. So now let's run the graph with the user input. What happens with the user input? User input is going to be passed here, and then we put it in the intermediate data. So the user input is going to be converted to uppercase letters, and it's going to be put in the intermediate data. And then in the intermediate data is going to be passed to the result. So the result will be processed intermediate data, which is going to be the user input uppercase. So the user input was hello world, and so therefore the result will be processed hello world in uppercase. So note that intermediate data is not in the output, right? Because we printed the result here, we printed the result of the graph execution, but we only have the result field in the output schema, because we're returning the output schema only. We don't see the intermediate data. So yeah, so that was all. And this is actually very crucial to understand because it's going to help you debug faster. A lot of people just they run workflows in LangGraph with the vibe coding, or they don't understand how it works. So by understanding these concepts, you're going to understand how the state gets updated and how the different workflows can be executed in LangGraph with super steps. And I hope you enjoyed it. Thanks so much for watching until now. See you in the next one. Bye bye.